Good afternoon. Welcome to lectures 59 and 60 on thermodynamics of materials. We'll actually pick up problem 4. To complete this, we actually found that we got the answer though, but explanation was not given properly. So I will take up this for the explanation. Briefly, I tell you what we did last class. The problem was calculate the vacuum required to cause decomposition of magnesium oxide into magnesium vapor and oxygen gas at 1873 Kelvin. So we considered the pertinent reaction and we did this. Then we okay, we have actually the equilibrium constant expression, and then another expression is stoichiometry. PMG is 2 PO2. Then we solve this and get the value of 6.39 times 10 to the power minus 7. But the actual answer will be less than that. This requires some explanation. But remember, one thing is this: this is our system. This is actual magnesium oxide, the temperature, and this is open. So whether it is open to atmosphere or what, or less than atmosphere. This was the question. Actually, the clue was obtained from this system, from this consideration in a closed system. Start from vacuum. The best way to solve this type of problem, consider a closed system, start with vacuum, and so there is actually no magnesium, no oxygen initially. So whenever they form through dissociation, since it is initial zero means it will dissociate. Delta G will be negative. So initial state which is non-equilibrium, then it starts dissociating and they will follow this stoichiometry, which is PMG is 2 PO2. This is the reason why it will follow. So considering this system, so this we apply, and of course it will sooner or later attain equilibrium, and when equilibrium, the equilibrium constant will be struck as given by this relation. Solving this two, this was the answer. Question is, it was you consider we consider this closed system, but this is an open system. And question is actually it will be what vacuum we will apply, etc., etc. So we have to follow this. This actually last day I took an analogy, but this analogy was inappropriate, was wrong actually. So today I will give you the analogy. Take up this analogy before. I remove this. This part I remove. This part, just this part. This consider analogy. Analogy part, remove this analogy part. I am giving you fresh analogy and correct analogy. Then you will be, I hope, satisfied. Okay, this you follow. This is, so consider analogy. Purely take up as an analogy. I am writing PMG equilibrium and 1 PO2 equilibrium. I am considering just example. I am considering this is actually, I tell you what, 32, this is 16. Example. This is a, so then if this is equilibrium value, this equilibrium, then what is then P K is PMG times PO2, as you have seen already. PO2 power half. I think you will be satisfied today. No problem. Absolutely no problem. So easy. Equilibrium, as you have seen already. What is this value? 32 into 4 perhaps. 128. And what is the corresponding PMG E plus PO2 E? E for equilibrium is how much? Tell me. For 48. My contention is this: if I make this equilibrium value, means this, based on this, these are this value is this value, and this value is this value. Okay. So if I make this less than this, then you have to appreciate that this product will be less than that. This I wanted to establish but could not. Failed actually in some cases. But today I show you. You properly consider this. So I consider, take an example. Consider now what happens. It is better. What happens? This is the question. Now next, now what happens PO2 to PMG times PO2 power half when PMG plus PO2 is made less than, slight space is less than 48. This I will demonstrate. I have already given you the answer, it will be also less. But quickly take, for example, EG, but we should take in twice stoichiometry. So I am taking PMG is, what is this? PMG is actually 60, what I have considered as 60. Yes, 16 I have considered, and the 9 perhaps. PO2 is 9, 18, and PO2 is 9. I think you have no grumble. I am taking an example. PO2 9, see twice as much. You have seen this twice. You have noted why, who is twice. You have no. PMG is twice as much. If half is here, it is not. Okay. So PMG is twice. This I have written. Okay. Okay, very good, very good. Thank you. So 18. This I have taken. So what is this? So PMG, hence PMG plus PO2. What here? Here what? 27. 27, which is less than 48, satisfying. This I have forced. Then corresponding, this is a check now. Now this leads to, and PMG times PO2 power half is how much? How much corresponding to this consideration? 18 times 3. 18 times, shall I write? 18 times square root 3 means 9 means 3 is 54, which is of course less than 128. What is this, sir? What is this? This is actually, this I am applying. I am applying less than, applied. Equilibrium, sir, equilibrium. Applied less than that. So these are all referring to applied. So PMG plus PM2 is applied. Okay. You may write, or applied. These are applied. So I write at the end. That means this is what? This is Q. And this is what? K is what? This is what? K. Q less than K. Q less than K. That means that is delta G is negative, because you have to satisfy somewhere. The one consistent principle, sir, that it is dissociating. So the reaction will ever. So this is okay. So I repeat this. Okay, 18, 19. You may consider another one. I take, for example, actually I am taking square root, easy square root. 9 is easy. 3, 4 you may consider. If it is 4, then it must be double as much. 8 4 combination. 8 4 combination gives you 8 into 2 is 16, which is again still less than, say, number of examples you can take also. So delta G, so the reaction is spontaneous. You just note this. So the reaction is spontaneous. All the time. All the time, then you'll understand what is the meaning of all the time. Achha, follow me. Now follow me. Why this answer I am giving? I will give you then. I have made this vacuum. Vacuum is necessary, and that must be, that is not this. This is not enough. Less than that. Maybe 10 to the minus 8, 10 to the power minus 9, etc. etc. So make this, the moment I apply this one, then obviously this product can never catch up 128, will fall behind 128 in the manner I have shown. So it will be Q will forever will be less as long as I have applied this. So less means delta G negative. So MgO always dissociate delta G negative. Always dissociate which you want. We want to produce magnesium. We don't want to retain magnesium oxide. No, that is against metallurgical thing consideration. We have come here to extract, not to unutilize. Okay, this is already MgO, okay, mineral ore. So produce, so continue. We don't want equilibrium. We upset the equilibrium so that reduction is feasible. So this is the answer. Forever. So So how long it will dissociate? How long? How long? Forever, eternity, forever. But MgO is not infinite amount. So as long as MgO lasts, the reaction will be produced. A reaction will be spontaneous. Mg will be produced. Mg vapor form. Remember, magnesium is a very important metal for, okay. It is used in actually Sg iron, you know, cast iron. You will study this actually, spheroidal graphite. This iron they use magnesium, okay, as actual modifier. So magnesium is used there. This is used in aircraft industry. Magnesium with aluminum. Okay, this is also used. Okay, so magnesium is very important metal. So vapor too you have to condense into liquid. Liquid further solidified. So you will get magnesium. Then from which you get, this is the other aspect where magnesium is used. The importance of these two are. This is actually what I wanted to discuss. This. So however, okay, this is good. Now you may ask one thing, sir. Very good, sir. But this is also interesting, sir. This closed system, this is open system. See how different is open system and closed system. Closed system, sir. This is also dissociating, sir. I started MgO dissociating into magnesium, vapor, and oxygen. So why not this? Then what happens? No, this actually attains finally. Yes, starts with full vigor, starts with delta G negative, very good, and this negative value gradually decreases. But negative minus 40, say minus, then minus 39, minus 20, minus 10. Finally, when it strikes equilibrium, 0 and stops. So, and in MgO is actually still unreduced, undissociated. Maybe very small amount has dissociated so far because of the values that we see. This is not our job, okay. So this is actually, we want actually forever continuous dissociation until the MgO is simply removed from the system. This is the whole story about this problem, okay. So but this gives a guidelines of this value. Any problem, anytime you come across this type of problem, you will try to solve this, okay, this way. That is, consider this value, guideline, what value it will be. Now why I am using this particular, this will be actually difficult to convince others. Why, sir? Okay, who tell you? Because maybe here some oxygen was there. Okay, vacuum. Okay, some oxygen in vacuum means air, low pressure. So oxygen is there. So this discussion might be with that. But then actually we have to consider start vacuum from vacuum. This is the value. Now whatever happens when you actually apply this will pass initial value, and continuously you maintain this type of thing. This product which is Q less than. This is the answer. This is the answer to the problem. This problem is solved. Okay. But I will actually tell you one thing. Instead of doing this delta G0 actual value I am giving, because at least this actually satisfies you actual value. Okay. Quickly. It will not take much time since you have understood the problem. You have understood the problem, so it will not a single page. Wait a bit. This will be helpful. But have I brought this? I have to. Yes, itself. So quickly take the data. So practical data is very useful. So what is the delta G0? It give me some time. Okay. So this is the delta. Now I am giving the delta G0 exact data, and I will solve it with this 730130 730 minus 240. Happy? This is the joule delta G0. Okay. Now delta G0 1873. If you have actually calculate, I am giving you this value here. Here I am giving the value. Okay. Why not remove this? Write this 348038. You can do yourself. 348038. 348038 joule. Okay. Good boy. Then it's this is actually minus RT LNK. You know very well. How many times I will repeat? I don't know. You are tired of actually this thing being repeated. R is 8.314 always joule, and T is the current temperature is what? Temperature 1873. Apply this, get K 1873 as this, and what is this value? Or telling K is actually this value. I tell you what, K value 1.97. Write this you write here. I give you the value calculations at telling K from this delta G0. K will be, you can check this 1.97 times 10 to the power minus 10. Okay, happy? So this is the product. This product is one equation, equation 1. This is the equation 1. PMG is 2. You solve this out, you get this. This answer I have already given. Okay, means this P total equilibrium, but equilibrium we don't want. We want to upset, disturb equilibrium, make it delta G negative. At least in these cases, PT. Problem solved. So no problem. Absolutely nothing is to be look at PMG P2. What shall I write here? This solution actually you can solve yourself. How you solve? Quickly tell me. How you solve this two? You substitute two unknown two equations. I will not say anything. Two PO2 here, then do all PO2, and you can get this value. And PO2 will, for your benefit, I give you the value also if necessary. PO2 will turn out as PO2. Solve this. Solve this. PO2 is what it will be. I'm giving solution. I'm writing you solution. PO2 is, this helps you, PO2 is actually 2.13 times 10 to the power minus 7 atmosphere. What is the PMG? Will you tell me what is the PMG? PMG is twice as much. So I am not writing. So PMG plus PO2 you can get this actually. 4. Actually it is in there. So thank you. With this, can I move on to the next problem? So I remove this one. So I remove from the bottom. Sorry. হ্যাঁ বড় দিতে হবে Can I remove this analogy part easily? Analogy part হয়ে গেছে. So this analogy over. This is the system you have seen, open to atmosphere, magnesium vapor is coming, okay, and then you condense it. I think you have got this. Ready? Problem next. Do this, and thank you. Now this all over. It's okay. একটু বেশি হ্যাঁ problem. Oh sorry, November 6th নাকি November 6th. Problem what? Tell me. Next problem is what? For what I wrote here? 4. Problem 5. Problem. Next problem. Let us write down the problem. Series of problems coming. Series for you. Series of problems, and all are important for you. Okay. Yeah, some of you are going to Tata, na? Tata. You see these problems actually. Find the minimum. This find the minimum number of moles quickly note number of moles, okay, happy, required to reduce 1 mole FeO. This is a blast furnace problem. 1 mole FeO to solid, actually solid, 2 Fe solid at 1173 Kelvin, and pressure is not given to you. One atmosphere I can give, but for some reason I'm not disclosing this P atmosphere pressure. You'll see it's not. It's okay. This is the problem. Find the solution. Now I tell you what. Write first of all the pertinent The pertinent reaction or equilibrium, whatever you call it. The pertinent reaction is, just tell me, a pure solid number of moles required to reduce 1 mole. Moles of CO. Thank you. Moles of number of, sorry, very good. Minimum number of moles of CO. Thank you. Of CO required to process. Thank you. The pertinent reaction is what? A PO solid plus CO gas is Fe solid plus CO2 gas. Now what answer will give? Number of moles. Let's consider number of moles required. To reduce 1 mole APO, what is your answer?
From stoichiometry it is what?
From stoichiometry, but that is wrong. Remember, this value, this answer is always dependent upon the equilibrium constant. When we say that it is a 1 mole, then that is a deep implication that equilibrium constant is considered to be infinity, which it is not. It is a finite value. So wherever you have used this type of thing, there it was, those reactions actually had very high equilibrium constant, like in acidometry and alkalimetry in high school. Sodium hydroxide plus HCl goes full, okay, because it was high equilibrium constant, goes to compressor. I'll give you deep connection between this question and equilibrium constant later about this value. So I tell you, no, actually it is not 1, because 1 mole CO, this is correct. If 1 mole of CO is used, then 1 mole of APO will be reduced. The question is how to make sure that 1 mole of CO will be reduced, 1 mole of CO will be utilized. For this you have to charge more than 1, so that 1 mole of CO will be utilized, because there is an equilibrium constant. You start with 1 mole, okay, then actually reduce, CO2 gradually build up, CO decreases, build up. A time will come when it will actually strike the equilibrium, and then there is no more reduction. When CO and CO2 both are there, CO is there, but it is in combination with CO2 and make the equilibrium ratio, and it does not proceed any further. That stops. So we intended that 1 mole of CO will reduce APO, but it will not. Okay, this you follow. Let n moles. Solution is this. Let. I'm giving you delta GZ is always necessary, so I give you A plus BT. This data, I'll give you later maybe A plus BT joule, as the standard format. You have seen number of times. Let n moles. Let me give the answer, then lot of discussions may be taken up. N moles of CO required. Then write. So write this. Okay, what is this? This very good. Delta T0. Okay, so I am writing APO once more. I am sorry that I have to write once more. Already wrote. That's in the problem. Solution. Oh, okay. Good. Let us write this. Solid. Plus you have to quickly. These are gas. I am not writing initially. What you have started with? What is? I tell you this. Suppose there is a box. See, this is a container reactor. You are taking actually 1 mole APO, 1 mole, and you take, since 1 mole CO is not the right answer, or you want to verify also. Let's add n moles n moles CO gas. This is the system, and temperature is, as he has given, what, 900 centigrade. Pressure is okay. So initially what happens here? Tell me. Here 1 mole. Initially moles. Moles wise, initially moles. 1. How many you have charged? N. How many initially? So no yet, sir. No CO2 yet, sir. At equilibrium. Moles again. Moles. What is this? Moles at and moles. Initially moles. In bracket. Moles. What is this? Your purpose is what? To reduce 1 mole into iron. So what it will be? Reduce fully gone 1 minus 1. When 1 mole gone, then how many gone here? 1 against. Now use the stoichiometry. If reaction is guaranteed, I will use stoichiometry. You should be actually be firm about this. Is a reaction guaranteed? Sir, what you are saying, sir, it is actually equilibrium. It is equilibrium state. Why? How the reaction is guaranteed, sir? So 0, how much? In -1 remains. How much is produced? 1, and 1 is. So strike equilibrium constant here. This is equilibrium constant. So equilibrium constant, write nicely. K is a activity of Fe. P CO2. Shall I write activity? I don't have to. No? Gas means activity is partial pressure. I ask you perhaps. Activity FeO. Activity of CO is partial pressure of CO. Okay. Now one thing at equilibrium. Since beginners, I tell you, I always, since you have a Q, K, business, so equilibrium is tag equilibrium. So activity FeO, you see the equilibrium condition you have seen. This is the initial. Okay. And you can write at the initial state. Initial. I'm not drawing this equilibrium. Easy to describes. So activity APO, how much? 1 mole means 1 pure stuff. APO is, you have to write this minimum, the term what's it? The requirement minimum, the term minimum. Okay, the term minimum actually corresponds to, okay, also implies APO is removed. Removal must is removed under saturation. Is removed under saturation. That is under saturated state activity unit, under unit activity of FeO. This is, you have to understand, and you will soon understand. That is right. APO is 1. Whenever I consider activity means relative to standard state, and for pure substance it is same. Pure substance same. Pure standard state is the standard state. No. So so 2 things I taught you. One previously, that is what I said. Metal plus oxygen is metal oxide. First problem. What I said, MO2 was not there, but it will be produced pure. Product produced pure, and this reactant removed, and that's produced pure, one activity, unit activity. Today it will be removed under unit activity. Removed, nay, it is not there, but still actually same whether it was present or not. It is just gone under unit. Before it was gone, 1.99 still there, means unit activity. 0.99999 still there, unit activity. Activity of pure substance does not depend on amount. Activity depends on amount in solution, mole fraction, solute solvent business, rare. For pure substance, no sir. No. So when it is just gone, still okay. So if you is not there, this I will further explain. From you note this point. So if you accept this, K, how will you get this K? Please tell me delta G0 I have given. Okay, this gives you, I am writing you, huh? K, what temperature? Interested? I am not writing delta G0 is minus or tell K. I am skipping those, huh? Because you are smart now, huh? Delta K is what? K, what temperature you are interested? Tell me. 11 means 900 degrees centigrade. This is your thermal reserve zone. You know, blast furnace thermal reserve zone is 900 degrees. So that's stack temperature. K1173K is how much? This value actually 2.3. But for simplicity, I am considering 2 only. Yeah? Remember, this equilibrium value is 2. I am giving you. CO2 by C will be C. So I am writing K is 2, and right here temperature, you may always stack temperature. No problem. 2. What is the PCO2 by PCO? You know very well. You know this. XCO2, PCO2, okay? This is, you know, NCO2, you know this. NCO2 by NCO, because, you know, and shall I in the P total, okay, NCO2 by N total, etc. Shall I write this XCO2? Shall I write? I can write this, but if you are interested, I am writing for you. Don't worry. Partial is mole fraction, you know. Mole fraction by N total means gas entry, and NCO will be likewise N total mole fraction. Then times what is this? Total pressure times this post-threshold pressure. So they all cancel, see. So that's why any pressure will do. P cancel and in total cancel. So what left? What left? Nicely, NCO2 by NCO. Again, tag equilibrium. No harm. Just you have to write on. Okay, this is all equilibrium. What is the value? Shall I put? Yes, 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 yes. Okay, tell me what is this? Sukolan NCO2 by NCO. What value I put here? I am solving this problem.
NCO2 is 1 at equilibrium
Ah.
and NCO is N minus 1.
Exactly, correct answer. 1 by n minus 1. That means what is the n value? You know very well. N minus 1 is, I am very sorry. K is 2. Actually, I have made a mistake here. Huh? I am very sorry. It's 0.5. Yeah. This CO2 by CO by, I am very sorry. CO by CO2 is 2. CO2 by CO is half of 2, inverse of 2 is 0.5. Please don't mind. This data, no one can tamper with this. Actually, 0.44, I'll tell you, 0.45. But I am considering here for simple discussion. 0.5 will help us. It will give us what? If it is this n minus 1 is nothing but 2. N is
3.
good boy. So you answer, see, got the answer. How many moles you will charge? 3 moles. 3 moles you will charge, then 1 mole APO will be reduced. Then 3 moles charge, 1 mole APO reduced. How much will be consumed? How much will be consumed? 1 mole will be consumed, and 2 n minus 1, 2 will be at equilibrium remaining in the system. So if I may draw this, okay, n is 3, okay, n is 3. For equilibrium state is what? See, follow. See, 2 moles CO, okay, 2 CO, 2 moles CO, 1 mole CO2, and tell me 1 mole Fe, no APO full gun, equilibrium state. Equilibrium state. This is initial state. Temperature 1173. This is the whole thing. Okay. So this is okay. N is 3. So this is fine. Under saturation. Now I will okay tell you something here. Very good. So what you should actually note here that note here you understood. See, start to I'm not writing so many things. 3 you start. Say follow the progress. 3 then next moment you have 2.9 CO and CO2 0.1. You say follow the reaction. 0.1 done, 0.1 produced. So 2.9, 0.1. Not yet equilibrium. Reaction goes on. 2.8, 0.2. Then similarly you will come at one time, reaction going on. 2, 1 and stop. So this CO, 2 mole CO, where is the utilization? No utilization. Similarly, you can guess actually if you started with 1 mole, then what would happen? Actually, if you this, so what is the percentage? Okay, conversion. 3 you charge, 1 is utilized. One third utilization. One third utilization means 33%. 33.33%. One third utilization. So 1 mole if you charge, say, simple minded you are. So 1 mole, then one third will be utilized. Means 1/3 mole CO, 2/3 mole of CO will left back at equilibrium, and 1/3 mole of APO will be produced, not 1 mole AP produced. 1/3 mole of APO will be reduced. So note here to make acha APO and CO will follow the stoichiometry. No, this is not better. It is like this. Note here, 1 mole of when 1 mole of CO is consumed or reacted, whatever language is consumed, or has reacted 1 mole of CO APO following stoichiometry, this is the use of stoichiometry. 1 mole of APO following the stoichiometry of the reaction as reacted, 1 mole of HPO will be reduced. But to make sure that 1 mole CO reacts, 1 mole CO consumed, we have to charge 3 mole CO. This is the, in nutshell, the message relation from this. To make sure you charge more, so that okay, so unreacted will be there. So, अच्छा, very good indeed. Okay, now I'll about draw a line here. About activity of APO. Discussion about activity discussion. Tell me, suppose what you have in the system. Tell me what you have in the system. This is the equilibrium system. So suppose you are interested to know the activity of APO in this system. Let me, it is better I draw. This is very good. 2 moles, etc. Okay, very good. So you are interested, suppose about APO. Acha, question. Oh, sorry, sir. Question. What is the activity? What is the value of APO? Sorry, value of APO in the system at equilibrium. In the system at equilibrium. Verify. You know, I have already stated that it is under unit activity. That is the concept of minimum. You will soon understand why it is minimum. Achha, what does it mean? Minimum 3. What does it mean? Can we charge 4 moles, 5 moles? Yes, sir. Minimum is 3, 4, 5, 400, 4 million, sir. So that is unutilized. That will remain unutilized and keep the system unsaturated with respect to APO. These are the things this will happen. So remember, this is the minimum, means actually that this is a requirement. It cannot be less than this. So what is the value of activity in the system at equilibrium? Verify. Verify whether it is A1. Verify whether, I have already stated whether it is 1. Whether it is 1. Verify. Quickly. How will you verify? Follow this. Write this. Consider this. K is, once more write. Please write. Write this one. You write this line. APO, AP, PCO2, APO, PCO. Right here. Equilibrium. You don't know. Okay. What you know, sir? See here. What you know? Is like this. What you know here? AP how much? Here. Equilibrium state. Equilibrium state. What is the activity of APO? APO is not there. So it is gone under saturation. No, we don't believe this. This type of statements we don't believe. We'll verify this. So let us verify. I put this. I don't write anything here. So unknown quantity. Now it is unknown. So APO is one. Oh, there's no argument. So it is present, sir. It is physically present, sir. PCO2 means what you know. What is can I write here? You don't mind. NCO2. NCO. So what it is coming as? What is the NCO2? NCO2 is, you tell me, 2, sir. 1, sir. 1 by APO is the unknown stuff. By what is the NCO? NCO is here, sir. 2, sir. 1 by 2. And K is how much already? K cannot be changed. Delta G 0.5. What is the value of this? APO is what? Turns out to be, tell me. 1 by 1 is 1. Sir, very good, sir. Yes, not present. So that is actually why this happened, because it was gone under saturation. Now you give another direct answer, sir. What's the no magic, sir? It's so easy and so simple that okay, sir, you consider one and find the value of NCO to NCO. This gentleman is equilibrium constant. No one argues delta G0. Oh, let alone. This is always okay. No one talks about it. So here you consider. Oh, remember this. I wrote here 1. Forgot to write here 1. Remember this. Under saturation. So it is 1. So you consider. So you get a value, and now you are putting this value. It will automatically come back 1. So no surprise, sir. So this is the idea. Now you will have the importance of this approach will be useful. Suppose you know 3 moles, you overused You actually cross the limit minimum. Suppose now you have charged. Now suppose you we charged or it was 4 moles of 4 moles of CO instead of 3 moles of CO. 4 moles CO instead of 3 moles of CO charged initially. Charged along with 1 mole FeO. Along with 1 mole FeO initially. Initially. Then what is the activity then? What is FeO at in the final state? In the final state, you will consider. What is the status? You tell me. You have charged 4 moles, so you can write this FeO quickly. FeO plus CO is Fe plus as before. Now here are the known values. FeO is 1 mole. Initial. 1 mole. How many? 4. 0, 0. At final, what? It is fully gone. How much it is? It is how much? 3, 1, 1. Okay. So what is this? Then what is the? This is the 3 moles and final moles. So what is this? You apply to this. What is the activity? What is the activity? This is also equilibrium. But see quickly. You write again. Fe. NCO2. I am not writing this. NCO2 by FeO. NCO at this value. What is the K? What is the Fe? 1. It is produced. What is the NCO2? Tell me. 1. What is the NCO? 3. What is the K? 0.5, sir. FeO is how much? Tell me. How much it is? FeO is going there. 1 by 1.5. Okay. 1 by 1.5 means 2/3. 2/3. What does it mean? Less than 1. So this is actually here. So this is not minimum. Is FeO removed under saturation? So in this case, FeO is removed not under saturation. Not under saturation. Not under saturation. What is that? That is not under FeO is 1. Now what are the implications of this? Tell me. Implications you tell me actually. What is the implication? Not so. What is that?
Not at A, FeO is equal to 1.
FeO is removed, fully removed. FeO is here.
Not equal to 1.
Not under FeO is 1. Not under FeO. Sorry. Not under FeO is. I am very sorry. What is this? It is less than 2/3. Sorry. It is 2/3. 2/3. 2/3. Not less than. It's less than that. So this is actually more than minimum you have charged. So what else you can tell from this? Tell me what else you can tell. So this is not this actually this if I drew this figure actually here actually where I wrote here. Yes, here I wrote. So what is the activity of FeO you have seen? So CO is not utilized. So what you will do here? You can charge. If you charge, here follow one by one. So this is the status. This is the first case. First case. If you charge more FeO, what would happen? Sir, at the equilibrium state, they say FeO is not seen. Let us perhaps charge more. If you charge more here, what would happen? No more reaction because it's already this composition is corresponding to unit activity of FeO. This calculated on the basis of this. So if you charge more than more means how many? 1.5 moles, maybe 1.6 mole, no reaction. So that extra moles, 0.5 or 0.6 moles will remain unreacted because there is no tendency of any reaction, because this composition, gas composition is in equilibrium with APO, and you are charging the APO, that is also activity 1. So it is already 1 and you are giving 1, so same activity, same gives free energy, so no reaction. So APO will not be further reduced. So this clearly shows that the system. This also clearly shows that that's no. Here what would happen? So activity is less than. So perhaps you can charge more APO. If you charge, that will react, because what you charge, activity of APO pure means 1, and what is present in the system, 2/3, 1 against 2/3, difference in activity means chemical potential, means gives free energy 1 greater, so they will interact and the reaction will further take place. It will not stop. So that APO takes place. How many you can answer? How many you can keep on adding? So 1 you added with 4 moles. 4 moles of CO is, I am not writing this, 4 moles of CO is capable of reducing how many moles of APO? 4 moles of CO, 3 moles of CO capable of reducing 1 mole. So 4 mole is actually unitary method. 1 by 3 times 4, 1.33 mole CO. So perhaps I can, with this gas composition which is non-equilibrium with respect to APO, solid APO, less than 1, so I can add 0.1, 0.2, 0.1 third moles, which 0.33 moles I can keep adding when it will be again unit activity of APO and no further. This is the whole thing, okay? This is about this. Very good. This part you have understood. I didn't write this much, but very good. This is okay. Now, next, take up this. Another thing I tell you, let me. Since I am discussing this part, what is this? FeO by CO by CO2 is what? 0.5. Let me complete this. Then, if necessary, I will discuss that one. Have you heard of chemical inactive zone in blast furnace? What happens there? Chemically, because what gas composition it has achieved? This value, this gas NCO2 by NCO, or this value is how much? 0.5, or CO by CO2, in fact 2, actually exactly 2.3. I don't know, this actually I consider simple, actually approximate 2, it is actually 2 by 3, this actually. So there are actually no more reaction, but this is good or bad? This presence of chemically inactive zone in blast furnace is okay, favorable or unfavorable? This is actually the hallmark of a modern blast furnace. This is very good. This is welcome, because then it says, okay, if you cannot be reduced, means you are actually in the right track, means you are sure this gas actually utilized, and then the gas that's leaving this APO interface, it is what this is? CO by CO2 2, CO by CO2 is 2.3 is leaving, that is capable of reducing actually the magnetite first, and still in the upper plane it is hematite, then it can reduce, so no problem. The problem, but what's the advantage of this? Suppose you actually, on the other hand, you consider that, sir, it is there is no such thing as chemical inactive zone. Sir, inactive, sir, why say inactive is very bad thing, bad term, derogatory term, sir. Then sir, 4, sir, what is the ratio? CO by CO2, just I should not write here 2, or more correctly 2.3. When it is 2.3, more than say 5, then you are leaving, when it is leaving the top gas, it is actually maybe 5, and it takes not much reducing gas for the 2 steps. They are actually very 11% and 22% reduction, not much. So it will leave say 4. So top gas say, so your chemical inactive zone is missing. So it is CO by CO2 is equilibrium. This is equilibrium. Equilibrium with APO. Don't push that zone. There it has struck CO by CO2. Okay. So CO by CO2 4. Let me discuss this. Suppose it is 4 or 5. Then what? No such thing. Suppose CO by CO2 is 5. I'll stop this part. Is 5, then what will happen? No, 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 no. So here, this corresponds to chemical inactive zone. CIZ I'm writing. Chemically inactive zone in blast furnace. Chemically inactive zone in the stack, actually, in blast furnace stack. In blast furnace stack. Well, let us write this point. This is a reference to this. See, I am showing how the implication of this thermodynamics with other subjects. Blast furnace stack. Suppose CO by CO2 is 5 at the stack, at BF stack, and 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 CIZ does not exist. Then what will happen? So when it leaves a top gas, suppose, and consider in the top gas, the exit gas, actually, in the top gas, BF top gas, which is you call exit gas, na?
Yes.
Exit gas, I give you that CO by CO2, you can consider it will slightly reduce. You know why reduce? It is rising. There is actually descending AP3 over AP2 stage wise. So it is some oxygen is, some CO is consumed. So as a result, this will be little bit down, CO by CO2. The more of, not so much of writing, is force exit. CO by CO2 is 4. Okay. See my point. So what the gas, you know very well, it is roughly 50% nitrogen. And this is here 1:4 ratio. You know 1/5 means 1/5 of 50 means 10:40. 10:40 though. So do you like this situation? Sir, chemical inactive zone, sir, we have destroyed, removed. We didn't like, sir. Always active, sir. If you is reduced, so then this will happen. Oh, always active, high, active, very active. Because what is the requirement? Critical is what? 2. Any value above that will reduce. Then what is the consequence? See the consequence. Okay, you should concentrate here. What is the consequence? 4. Now, how do you like as a blast furnace? Okay, blast furnace. Okay, okay, blast furnace operator or blast furnace engineers. Okay, what is the prospect of the CO by CO2 4? So this could reduce, sir, if you further this just any value above 2. So unutilized. And where did you get this so much of CO by CO2? By burning carbon at the 2 year. So coke, high demand of coke rate, and bad management, and badly efficient blast furnace. This is old type blast furnace. In the modern blast furnace, you have CIZ. Means you made sure, okay, Baba, if you are, this will never be greater than 2 by 2 index rate. So you cannot claim that, you cannot accuse that your top gas is was capable of reducing APO further, which you have not used. Burn carbon and now reduce APO. You could charge more. Either burn less carbon at the 2 year or charge more. You have not one, charge more in the from the top of the blast furnace charger. Okay, bell, double bell practice. So there you charge more. Either you have not done, instead you are wasted carbon. You are reducing gas, you are wasting to the atmosphere. Understood the problem? There is implication here. I don't want to go further into this. I don't want to draw, but this is good enough. But this problem has been solved. But still, there are 2 more things I have to tell you. Efficiency of utilization. This actually next you take up. Activity you understood. Activity APU is less than 1. All of this. Good boy. Good boy. Good boy. Very good. Now take up. Next point. Okay, the note here. Stop this part. Let's take up this one. Another point. Good boy. Okay, what is another point? Is the efficiency of gas utilization. Gas here, CO, reducing gas. Reducing gas, right? Achha, gas, right? Say reducing gas utilization. Gas utilization. Say reducing gas, oxidizing gas, in case of reduction, reducing gas utilization. That is CO utilization. And percentage typically we report efficiency. So what is this? percentage. What is this? Tell me. Common sense. Common sense is what? Tell me, sir, how much is utilized and how much I charged. The ratio, sir. I charge 3 to make, I asked that I use, be fully used, like that's why Carnot cycle efficiency. Heat given at high temperature, but how much work is obtained. Okay, that ratio. So write moles of gas input and moles of gas utilize times 100. What is in the present case? In the present case, right? In the present case, eta CO in percentage is what? How much? In the present case, tell me how much you charge. N moles you initially said, but you know the answer. How much? 3. So 3, and how much utilize? 1 times 100. So 33.3% efficiently you use. 33% efficiency. You cannot increase this unless, so think about this. So this is your answer, efficiency of gas utilization. What is this? I tell you what, I give you this. Efficiency is 3. Actually, I am writing in 1 by n minus 1 to. Efficiency of CO is 1 by n minus 1. Okay. Achha, very good. Efficiency is 1 by n minus 1. Why is that? All nonsense. 1 by n. Tell me. 1 by n. 1 by n. That is 1 by n to into 100. Keep on. Into 100. 1 by n. Achha, what is K? Note, K is what? Note, K is what? Tell me. 1 by n minus 1. Take a look and answer. This previous problem. K is 1 by n minus 1. So what is, I want to, achha, what is my purpose, then you will understand. Achha, this is one. You box this. This is the first. This is called, actually, what is this called? Okay. Basic relation, okay, or say simplest, okay, or direct relation, okay. What is, okay, very good. So what is the K is 1 by n minus 1. I am going to get. So now we are trying to find the relation between efficiency and equilibrium constant. Between efficiency eta and equilibrium constant K. Okay, so right, see, you do yourself. So what is the efficiency? You forget about the percentage. Last I'll give this. Eta CO is, I'm writing 1 by n. Last I give them times 100. 1 by n. What is K is n minus 1? What does it mean? What is this? N is what? This gives you n is what? Tell me. N minus 1 is 1 by K. Okay. Or n is 1 by K plus 1. What is this? 1 plus K by K. Remember, K is the equilibrium constant. So what is 1 by n? Is nothing but K by 1 plus K. This is your very much times 100, right? Times 100. If you percentage, efficiency percentage. Oh, unnecessary, no? Efficiency. As you understand, it's okay on times 100. So K by. So you want to increase the efficiency. This is very poor efficiency, 1/3 efficiency. Who is responsible for this? How to improve upon it? Now you see, sir, equilibrium constant. You are metallurgist, you are actually in a blast furnace job. How to improve this? Sir, what you will do? You say, sir, equilibrium constant, this reaction actually inherently have low equilibrium constant. Such equilibrium constant as this much is the maximum that you will get. For this reaction, this is the main, remember, this is the main reaction in blast furnace. In the blast furnace stack, other 2 steps are contributing to a much less extent. So this is the main thing you consider. So you can see, if equilibrium constant increases, efficiency will increase. How will you show this? I tell you what, you can see this. it cast in a different manner. Divide by k, then you will have interesting result. 1 by k plus 1. So what does it mean? If k increases, so this obviously leads to what conclusion? If k increases, equilibrium constant increases, efficiency increases. Very interesting, important. See here, from here, k increases means this gentleman called decreases in the denominator, and denominator decreases means whole thing increases. That's why increases, efficiency increases. So one root is one answers are increase the equilibrium constant. But for this reaction, who will change the equilibrium constant? You can have some answer. Equilibrium constant is a function of temperature, sir. So work with the temperature, sir, then possible. Okay, okay. Or maybe if there is any other reducing gas, look for the equilibrium constant. It better. But this is, see, which yes, Anurag, why I wrote this way rather than this way? This also, this is clumsy because k is showing in the numerator, k is showing in the denominator. Oh, remove this. This is that. Okay, so you are sure. Okay, now very interesting. That's I am removing this. Removing this. Remove this, and I'll tell you some important quick answer. You see, just I'm writing from this. Okay, so write this. Start from here. So start from here. So start. Okay, K is what efficiency is. Efficiency is right, or you write that. Efficiency, I mean, with COMG at similar reactions. CO, what K by 1 plus K. So, table, you make a table for your benefit. So, in this case, eta CO. Actually, it is not M, eta, okay, efficiency. What is similar relation, right here, right, complete this. Similar relation holds, same relation, okay, similar relation holds for other reactions, same relation, similar relation holds for other reactions with same number of moles of reactants as products. Same number of moles of reactant as products means O1 and O1. Reactant gas. This is about gas because activity of product. Example, another example. Tell me another, sir. One I'm showing million you can generate, and if some doesn't fit, then you have to do this way. The way I have done. The way relation have generated relation. So this relation, for example, I'm giving the example. CO2 plus C is 2CO. 1 mole against 2 mole. No. This formula will not work. But similar reaction. Think of similar reaction. FeO solid plus hydrogen. FeO solid plus hydrogen gas goes to Fe solid plus moisture. Happy? And similar 1:1 gas. Okay, then this is a relation. Okay, but not. Then you understand, not CO2 gas plus so-called boudoir reaction, or say carbon gasification, CO gas. You understand? 1:2 gas. No. You have generate. I can show you how to generate and this, but this is actually unnecessary. But yes, some comments. Table you follow. Equilibrium constant and eta. Equilibrium constant says reference. Reference is what? K is 1, sir. 1. At a temperature, is function of temperature. Some value it will be 1. Now it is 0.5 by 1. So 1, what is this value? Efficiency is how much? 1, good boy. What is it? 1 by 2. 0.5 means, okay. 0.5 is, we actually, percentage. Percentage is leads to 50%. 50% satisfactory, sir. 50%. Good. Increase this. 1, 2, say 2. 2 will be 2/3. 2 will be what? 2/3 means 2/3 leads to 0.6 is 67%. See, increasing. If it happens to be. So depending who can change equilibrium constant? I tell you, sir, equilibrium constant. Why you are writing, sir? You are bored and you are pen, you are writing. Who changes, sir? Sir, if the reaction changes, equilibrium constant varies from reaction to reaction, or for the same reaction, who changes? Temperature. Temperature K is function of temperature alone. Like delta G0 is a function of temperature alone. By definition, I'll teach this in the next topic. Okay, good boy. 2 is fine. Then 10 say jump into 3 maybe better. 3 sometimes 3. Just 3 4. Good boy. So 75 you are happy. You should be happy, sir. CO is utilized more. Which you want? What you want to think yourself. Ask yourself what I want as a metallurgist or as my job. So this okay. Then 10 will be ball. Tell me 10 by 11. Do this 99 9.1 91% cake. Take a look 91% perhaps. 10 na 10 by 11 koto 10 by 11 sorry 0.10 0.91 no correct 91%. Make it 100 it will be tell me 100 by 1. So it is how much roughly approximately there 99.9% I'm giving. So like this. So 100 up to 10 is 90% means you have hit almost 100%. And 100 here 99.9% and then 1000 will be 99.99. Decimal place is improved only. But so you have got this basic thing. Take the opposite picture. That is maybe. So equilibrium constant 100. Okay. You know equilibrium constant actually now keep again start another table. K okay sorry K start again fresh start over in a downward fashion. 1 what it is 50%. Look at it 0.5 leads to 50%. What is this another one less now 1 0.5 sir 0.5 equilibrium constant is less than 1 0.5 by ball 0.5 by 1/5 means 1/3. Look at it 0.5 by 1/5 is 1/3 into 100 means 33%. See, it was increasing, it is decreasing now. 0.5, then 0.1 perhaps. 0.1 perhaps. 0.1 means actually 0.1 by 1.1. So you do this. Yeah, this leads to 1 by 100 means 1 by 1. 100 9.1%. Okay, 100 by 11 is 9.1%. Okay, Ajal. So 0.01. 0.01. So what? Tell me. 1 by. I made a mistake anywhere. 1 by why I am writing. What is the equilibrium constant? 0.5 can full coach you. 0.5 by 1.5 is okay. Then what is it? I have a mistake here. It is 9. How can it? Oh, correct. I'm sorry. This point was there. Correct, 100% correct. So this is 0.01 by 1.01 into 100. So it 0 point close to 0%. No, close to 1% ball 1%. It's 100 too. 100 1 by 1.01. 1 by 1.0 means 1 by 1. So 1%. Okay. So you see 1%. Only 1% conversion of the gas. CO gas that you charge, 3 moles you charge. Let's say okay, so 1%, that 33%. So you have to consider. Or say 1%, 100 moles you charge, 1 mole will be utilized. 1 mole you charge, how much will be utilized? 0.01. So this goes on, even less. Okay, this one even less. So you should have an idea. So here cutoff is probably 10. 10 means satisfy 90% conversion. I have a feeling very useful. I didn't know this. Later on I thought only, and now it is actually 0.01 is actually okay, 1% means now actually it is awfully bad, and okay, it should be avoided. Okay, and it's not helpful. So this part is over. So efficiency of utilization, you got this idea. Anything I missed out here? Anything? Okay. Last. One thing I tell you, this is actually in this context. I remove this. All this. This discussion is not there. Just your if you have any mental block, remove now. Okay. So I said. So we found that APO is maybe removed under saturation. may be removed. May be removed under saturation. Under saturation. What is the meaning of this? APO is anytime A means relative to. Relative itself. Relative itself. Pure solid. APO is, so APO, so thing is APO is not there, but still activity. So like that. So that is, so APO is physically not present. It was solid, 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 solid. Solid, these pens are very good. German. APO solid is physically not present. Is physically not present. Yet activity of APO is 1 in the system. This is very interesting, and this we have understood. Verify number of ways. Okay, very good. An analogous situation. Is a another practical analogy. Practical analogy. You enjoy this to distinguish unsaturated, saturated, saturated, right? In presence, or two types of saturated, or in absence of solute, and last is supersaturated. So if you have any difficulty, you clarify this whole life. Supersaturated solution. Solution of a solute in a solvent. E.g., example, sugar water system. Or salt water system. Sugar is solute, solvent. I think with the previous discussion, you will very easily follow this. But it is so useful. I take a beaker, just a ordinary beaker. Temperature I am giving. Temperature, for some reason I am giving temperature 100 degrees centigrade. I raise temperature 100 degrees centigrade. Beaker. This is a beaker. Beaker. So to show you that it is a very trivial experiment. What I have taken here? Water. I'm giving water. So I'm adding here, pouring into this sugar particles. Okay, sugar grains, sugar particles, sugar powders particles. I add this, okay, like this, particles now dissolve. I don't see sugar. Means this is a case of easy case, commonest is what? Unsaturated. You don't see any sugar. Different color will help. Today actually remove this one, but this may be helpful. It is better. Hey, hello, red one. I just see there. Down the red. Open the red. No, that better now. দেখতে পাচ্ছিস red color. This will be striking. Okay. I didn't think of this. Then otherwise I would prepare. So I am removing this sugar actually red to contrast. Sugar added. So it is not seen. Solution, sir. This is still not solubility limit reached. We say saturation limit, solubility means actually saturation value. So what is this? This is what you call this? Unsaturated solution. Okay. The next case is case 1. Case 2 I am drawing again drawing. It's not difficult. Draw this same way. Second case, draw nicely. Good enough. And water again, temperature same 100 degrees centigrade. Important. This temperature will be important later on. Then what happens? I am giving this. Again I am adding. Again sugar particles. Sugar particles I am actually adding. Okay, drop particle. Then again also you see, I don't see. I don't see. But I say beforehand I tell you, this is actually saturated solution. I tell you. Why? Why I will clarify this? No, not sin. Saturated solution of sugar in water. That is a syrup. Syrup. Saturated solution, answer solution of sugar in water. Of sugar in water. Of sugar in water. Of sugar in water. Right here, although solid sugar is not visible in the solution, okay, is not found in the is not found in the is not found in the system, okay, solid sugar is not found in the key, what should a solution I should not write, is not found, is not found to settle, is not found to settle. Third, I have some space, no problem, just little bit this side, again same, water, 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 water. Again I do this, now another 3 as if, so I just spec another grade, fourth, as if I added, and I found this one, the extra one that I added just now is reporting here, is settling here in this. What is this? Okay, what is this? This is sugar particle, right? This is sugar particle. Is not dissolved. Sugar particle which is not dissolved, which is not sugar particle, solid sugar particle, okay, this is understood. So this is what, this is which solution, this is also saturated, obviously this is saturated, everyone knows that sugar is sitting there saturated, that's why it is not a solution, water solvent is not able to pick up any more sugar, solubility limit has reached, so that's why it is not picking and it is leaving, and it is what it is not just going down and is sitting at the bottom. So this is also saturated solution, and sugar is found to settle, now this is good enough, super saturated I consider, this is important, okay. What's the difference, why this, which is a saturated, saturated solution, which the one when this settling is imminent, that point means when it has happened, you know that saturation has occurred before it. That's why it is not, solution is not, water solvent is not able to take up any more sugar. So it has happened before. Activity here, the activity, language of activity of sugar, solid sugar is 1 with respect to itself. So 1 is already, though not physically seen. And here physically seen, so everyone goes, oh, it's okay, he's seeing that, what are you talking? But the mind says, the moment it is seen, no, it has happened before this, so prior to this, okay. So this is actually, these are, I'm writing this, activity of FeO is sugar, activity of sugar is 1, activity of sugar, obviously 1, sugar here, okay. So this is which case? FeO is removed, you don't see FeO in the system. FeO plus CO, Ap plus CO2, Ap is just removed under saturation. This is here it is produced, that is removed. But you see, I don't see, when I don't see, still it may be 1, okay. So it is at saturation, or it is, okay, what you say, saturation is just reach the saturation, right? Just reach the saturation. This state, and what you write here, saturation has occurred previously to this. This you report. The saturation has occurred previously to this. That is in case 1, case 2. This case 2, case 2, case 3. Previous to this, that is in case 2. Case 2, okay, in case 2, that is in case 2. This is case 2, case 1, case 3. This is case 3. Now, if you have add more and more, then it will be what kind of solution? More and sugar will be there. What it will be called? Now, this saturated, not supersaturated. This is sometimes this misconception. No, the solution is unaffected. It doesn't know sugar is sitting separate phase. No, no, no. Same activity. Sugar has a unit activity and solution which contains sugar also unit activity. That's why they are equal. And any more addition, any amount of addition will not change the situation. But what is supersaturation then? Interesting. You follow this. This is very interesting. And last is this. Then last. Okay. What I'm telling you? See. Okay. So yeah, it may be better. Hmm. Okay. Better. It's saturated. Maybe here also, or okay. Here better. Case 4. Suppose starting from this state, what is the state described as? Temperature is, tell me, 100 degrees centigrade. We reduce the temperature. Temperature is reduced to 50 degree perhaps. Reduced to 50 degree centigrade. It is 100 degree centigrade, right here, everywhere write 100 degree. This gives you what? What is the name of it? Solubility. You understand, na? Solubility. This is solubility. Saturation, solubility, saturation, unnecessary term. Solubility means saturation, like vapor pressure. Vapor pressure means saturated vapor pressure. So same, both all are thermodynamic. Temperature reduced to 50 degree, then what would happen? 50 degree centigrade. Now, one thing you must know, it is related to as temperature decreases, solubility decreases. This is form of thermodynamics, right? Equilibrium constant. Temperature increases, K increases, decreases. It is equilibrium. This is a chemical process, thermodynamic process. So, for which solubility is less to 50 degree centigrade, right? 50 degree centigrade. For which solubility, the solubility, right? This is less than at 100 degree centigrade. What is your expectation? The solubility less, but you have already saturation this 100 degree saturation, 50 degree of course above saturation, super saturation. But then what should happen? It should. So see the how it should. It says 30%, 30% saturation, and 50 degree centigrade, so 20% saturation. So 20%, so it will come. Will try to come to that. But it is equilibrium value. Come down to 20%. How it can go? By throwing the solid sugar into the water, into the system. But for kinetic reason, it cannot sometimes. For kinetic reason, slow kinetics, it can low temperature, it cannot get separated, so it remains in the solution. So 40%, 30%, 30% sugar is still remaining at 50 degrees centigrade. What is this state called? 30 degrees. Can I remove this? Remove this. Sorry. Supersaturation continued. Right here. Supersaturation continued. Supersaturation. Let's complete this. Continued. Give it this. Case 4. Like a case 4. So that you have no difficulty. Supersaturation. That's case 4. Supersaturation. Right here. Supersaturation. Topic. Supersaturation. All right. Continued. Case 4. Case 4 continued. Consider solubility of sugar or saturation of sugar at 100 degrees centigrade. Sugar in water. Sorry. Go slow. Go in water is 40. 30%. I said, 30%. Say. Start. Consider. Assume. Let us assume. I don't know at all. Let us assume that. Is 30% at, tell me 100 degree. 100 degree centigrade. Okay. What does it mean, by the way? Again, every term, 30%, what does it mean? 100 gram water, 30 gram. 100 gram water means water, we don't go by gram, cc. Density is 1. 100 cc water can take up to 30 grams. Then this is, and solubility of sugar in water is 20% at 50 degree centigrade. This is actually known. Note solubility always decreases. Note solubility always decreases with temperature. Like equilibrium constant with temperature. Right? I am writing you energy like equilibrium constant, right? Equilibrium constant decreases increases with temperature, or decreases, right? Decreases with decreasing with them changes with temperature, like equilibrium changes with temperature. That is fact. With temperature, don't worry. Good enough, I've said. Now, when this is taken to 40, case 2 is taken to 50 degrees centigrade, what happens? It should separate some sugar. It should deposit some sugar, because 100 cc 30 gram was there. It should be 20 grams inside. 20 gram where? 20 gram where? In the solution, sir. Don't see here, sir. They are solid. No, in the solution one, another is physically present water. Just weight perhaps at the most. Nothing else. But separate phase, sir. So it should be 20 grams. So 10 grams of sugar must come out and report and should be deposited as solid. But if it does not occur, but it may not occur for slow kinetics at low temperature of 50 degrees centigrade. So in that case, it remains there. And this is actually non-equilibrium case. Your equilibrium is what? 30%. At this temperature, not 30%, 20%, but you are holding more than 20%. So it is an supersaturated case. So it is but now at 50 degrees centigrade, if the extra sugar, that is in excess of solubility, in excess of solubility limit does not come out of the solution of the solution in case 2 of the solution as obtained in case 2 saturated solution, 100 degrees centigrade. Case 2 does not come out, it remains. What is the reason? For kinetic reason, perhaps. For kinetic reasons. For kinetics reasons, for kinetic reasons, okay, the solute, the sugar still remains in water, making an tell me, and making a supersaturated solution which is a non-equilibrium state. These are equilibrium values. Solubility is an equilibrium value. These are equilibrium values, okay? Thermodynamic equilibrium values. Okay. Supersaturation solution. Okay. Making a supersaturation which is a non-equilibrium case. Non-equilibrium, right? Or metastable, they call non-equilibrium case. But sooner or later it will be, time permitting, it will come down. Okay. So as long as it is not happening, it is no separation, it is a supersaturated solution. Okay, see the point. Okay. So it is actually about temperature. Okay. or you may write actually, okay, is a non-equilibrium case. Okay, ठीक है. Okay, actually it can be shown further in terms of activity, but I'm not taking up. This is non-equilibrium case. Example, very good example is what? Supersaturated solution, Martensite. Martensite you read, Martensite, number of times, austenite, quenched, the same 8.8% austenite or 0.7% quenched, then it will actually cannot liberate this carbon solubility at the room temperature was only 0.0025 in iron, alpha phase. Okay, but as at this room temperature kinetics is so slow, it cannot come out, so it is a supersaturated solution of this. So it is a unstable phase. In non-equilibrium case, unstable phase, unstable situation, unstable, okay, unstable phase, right? Unstable phase. Right? So what will happen? Sooner or later it may come out. If you allow 1 year time, then it will come out perhaps. Okay, so fine. Okay, or it will be heating gradually. Heating, then you will see ferrite and cementine starts coming out. Means equilibrium one. See your equilibrium iron carbon equilibrium diagram. That's why it doesn't have martensite. Doesn't have martensite. It is actually the ferrite and cementite at the room temperature. See my point? Okay, so I think this is enough of discussion. So you have actually understood this case 1, case 2, case 3, case 4. So this is, so can I remove this? I can move on to the next one. Okay, is okay. Anyway, there's a lot of discussion here. I have touched upon many of them, particularly blast furnace and efficiency of utilization, gas efficiency. Now, so at one, do you want to open the windows? Huh? It's okay. That's fine. 6, problem 6 quickly. Each problem is actually unique. So it is actually representing one group of problem. So see, you see now another new feature is always coming. Okay, this problem is what? Let us discuss this problem. Okay, sir. Okay, sir. Okay, sir. Good boy. See what is this? Let us. Solid zinc oxide, solid zinc oxide, and zinc sulfide, and solid zinc sulfide. This is right. Write this correctly. Solid zinc oxide quickly. Solid. Since I am copying down the problem, actually I should have written on the side. No, this is better. Then I will get this side. Problem. Problem 6. I will use this actually. Problem 6. Write this. Solid zinc oxide and solid zinc sulfide are equilibrated. Are equilibrated. Equilibrated. Solid zinc sulfide and solid zinc sulfide are equilibrated at 2000 K. Yes. 2000 K. Go slow. Go slow. Go slow. Hurry means all disturbed. Sorry. With H2S, H2O, hydrogen, H2S, H2O, hydrogen, okay, mixture, okay, happy? Then what happens? Given at equilibrium, pH2 is 0.5 atmosphere, pH2 is 0.0421 atmosphere. Calculate the given. Calculate the PO2, pH2, pH2S, and PZN in the equilibrated system. In the equilibrated system. This is the problem. Okay. So I tell you, follow this. I'm sketching. This sketching is very important. This is my. I'm drawing closed system unless. Actually, one thing. See, categorize your problems. First, you learn what? First problem, feasibility. Whether material will be oxidized. Yes, no type. And at a given state, delta G. Next problem is likewise, FeO plus CO goes to Fe plus CO2. Next problem, if you remember, similar type. Feasibility. Third problem is not that. Because you are actually CO and hydrogen 1 and 3. What is the equilibrium composition? To find the equilibrium composition, another aspect. Fourth problem, magnesium oxide is to be reduced to magnesium. What is the vacuum required? It is not feasibility. Ask give me the value of the vacuum required. Involves lot of thinking, okay, and like it said, calculation as well. Third problem, fourth problem. Fifth problem is what? A minimum requirement is what? Concept of activity of which is actually removed under unit activity. Minimum requirement and efficiency of gas utilization is a great issue. Great issue also. So this you have actually learned. This is suddenly a different thing. Is what? Number of solid phases, and in the phase this is actually start, initial state. Zinc oxide, solid, zinc sulfide, solid. Try to distinguish this. And what else you have given? H2S, three gases you have charged. See, follow. H2O, hydrogen. What temperature? What temperature? Tell me. 2000 K. 2000 K you have charged. This is what state? Yes. That is very important. This is what state? This is no. This is are equilibrated at this with this mixture. Equilibrium means you take this, take up this one. Equilibrium you have at equilibrium given later. Okay. So equilibrated the initial state, non-equilibrium in fact. Initial non-equilibrium state. Initially you have charged this and with this gas mixture. Then what happens? Goes to draw this. What is still zinc oxide? Although have reacted, but still unreacted stuff. There. What else are there here? Tell me. All possible gases. You can guess these three obviously, and additional two gases are coming. So what are they? Other things they have introduced, like this sulfur and zinc. So right, equilibrium final or equilibrium state, temperature remaining 2000 K. This is your problem. Okay, good, very good, very good. And okay, so you have to give in to you to help perhaps, or otherwise pH2 equilibrium. pH2 equilibrium koto? Which one? I'm very sorry. Equilibrium is given to you 0.5 atmosphere. Given another one, hydrogen is how much? How much? 0.0421 atmosphere. If you want water, water. H2S, H2O, hydrogen. No, I have written correctly. H2S, H2O, hydrogen. How many? 3, 5, 4, 5, 6, 4, 5, 6. Thank you. O2. Thank you so much. Oh, how could I miss this? 4, 5, 6 is necessary. Okay, good. Okay, so this you have to find. Of these two are given to you, pH2O and pH2. Okay, these two are given. Just start. Start attack the one I missed. Okay, solution. Right, solution. This is the solution. Already started. Consider the equilibrium. Follow this. This is again new concept coming. Easy though. Easy though. Consider the equilibrium. Which equilibrium? Suppose you are interested to, I tell you, PO2. So you have to find all these at equilibrium. So what is the question? Question is what? I'm telling you. I'm telling you. Tell me, P, which are given? PH2S, how much? PO2, how much? P zinc, how much? And what else? 3, 4. Fourth is what? P hydrogen is given PH2. PH2S have written PO2, P zinc, P sulfur at equilibrium. This is the problem. PR problem. Okay. So now consider the equilibrium. Follow me. I'm writing this H2 plus H2 gas. I'm writing for you, but I have to write it. I have a habit, a double habit of writing because gas, solid, liquid, this okay. 2 plus half very good, very good. Delta G0 will be available. No, see, you have to actually argue, delta G is available in the form of A plus BT. I'll give that data, this one. There is the equilibrium constant for this, okay, delta G0, I'm helping you. Delta G, I'm solving this one, first one, PO2, at equilibrium. This one I'm trying to solve, PO2. See how I'm doing this. Delta G, what temperature you consider? Tell me, 2000. Is out, since AB or known, I'll give the data soon. This leads to K2000, equilibrium constant is known. This is known, hence equilibrium constant is known. What is this? Tell me. Let us say Nirjor. Let us try Nirjor. K equilibrium constant is known. Delta G0 is known. K is known. Why? How it is known?
Due to temperature.
What is
Constant.
what is that? What is that?
Function of
And function is known. Why you have to mathematically find. Minus RTL 100 times every day. Maybe 1000 times maybe. Every day. This number one relation in thermodynamics. And what is this? What are doing today? Today is the culmination of our study in a sense. Why you have taken up such a course as thermodynamics or metallurgical thermodynamics or thermodynamics of material, so that we may solve such problems as we are considering now. These practical problems, these industrial problems, these research problems. If we can show that we are able to solve them, and similar such problems, millions of such problems we can solve. This is the purpose. These are all our preparatory. Today is the time we are actually applying this. So good boy. So what is this? Can I write? pH2 by pH2, PO2 power half. Equilibrium you can tag all the time or depends upon now. Since you are gradually getting veteran. Okay, pH2 is how much? Tell me, giving to you to help you. 0.5 hydrogen how much? 0.0421 times PO2 power half. Then what will come out from this answer? 1 is out. Now I tell you what I did actually. Why I consider this equilibrium? I actually made use of, took advantage of this. Oh, H2 and H2O. So why not link up with oxygen? If you are interested in oxygen, finding a PO2, consider an equilibrium involving oxygen. Otherwise, how will you ever get oxygen, partial pressure? So involve oxygen, and with H2 only possibility is this equilibrium. This reaction is not given to you, but you have to consider this equilibrium, and the rest is easy. Delta G0 will be available. This one. And another thing I tell you, sir, this is so many things are there. You are what are you doing? Understand? I don't understand, sir. Sir, H2, so why not sulfur? Yes, sir. Why not H2, sir? These type of stray questions. When a student is asking means he is in the right path. He will learn. All so-called random questions, or what to say, actually insensible questions, maybe you may call them. The whys are not this. This actually I faced myself. I did. I asked myself this one. Why not this? I tell you what. Answer is this. Anything with anything. Equilibrium means all kind of reactions under equilibrium. When an equilibrium state is achieved, all possible, I'm writing you, all possible reactions, all possible reaction is under equilibrium. If one of them is not, it is not full equilibrium yet. All possibles are with all of them together. No, any number. 2, 3 perhaps participating, 2 participating, 4 participating. This is the message. Bas, problem is over. There is no other problem. For example, what I did here, if you ask me what I did, see, I'll show you. Color chalk is helpful. Let us keep it up. What I did here, you know, I show you. Any with any. So, H2, I picked up these 3. All equilibrium though. Full set is equilibrium. I wish to consider this. So, I may find out PO2. I complete this with the data, practical data now. Practical data is helpful for you. So that will, since I have this, I will not do this for the other ones. This I will completely show you. Delta G0 is A plus BT, exact values. Exact value is, shall I make a room here? Delta G0 is what? Minus 2, 4. Good boy. Minus to write this data. Data very useful. Why will you get, when you practice actually data, very, you get data book, but it is better you get ready here. 1000 plus 54.8 T joule. Happy? Happy to? Delta G 2000 you will be able to calculate very easily. Calculator is needed. And that value will turn out 136400. Right? With me. 136400 joule. K is what? Use as, yes, Anirjor, I was asking you. Delta G0 is minus RT ln K. Shall I write? R is how much? 8.314 joule. Since joule, T is how much? Temperature 2000. So you get K. K is how much? You must be interested. Is what I tell you what K is? 36.52. 36.52. If you do this calculation, you find yourself PO2. Any problem? 36.52 everything though. PO2 is what? 1.058. Now, this is the answer. 1.058 times, oh sorry, times 10 to the minus 5, and also answer. Box this. One answer out, right? Answer. One of how many? How many are there? 4 there. And 2 already given to you. 2 is gifted. Oh, this is gift. This is what? This value is where? At equilibrium. This is here. See, Lena, initial has not given, and you don't bother. Use an equilibrium constant. Equilibrium constant applies to reactions at equilibrium. Good boy. So right. So right here. Note. Reading at times may be helpful. Note. When a reaction, oh boy, this is not so good. Note, when a reaction system is under complete equilibrium, note this, all possible reactions under equilibrium, not that a selected few under equilibrium, all. Sometimes if anyone is missing, we give a new term called partial equilibrium. But complete equilibrium is saying it's not partial. So be careful about this. Hey, oh, thank you, has come back. Good boy. So good. Okay. Now you have to propose. Now actually I have written many things. PO2. Next, suppose I am helping you. What you will pick up? That is also a good idea. What you may pick up? Oxygen is out. What you may pick up? What you may pick up? Oxygen is out to help you. Remember, solid is very helpful. Because activity is 1 always. So, and also another thing, these are tips. Solid helpful. Formation reaction, small reactions, helpful because we don't have many terms to handle. 2. And what else? I said, and of course, which will be pertinent. For example, say oxygen is out, you may consider, I'm actually giving leading question, say zinc oxide. Then what you will get? Zinc oxide. Solid is there, na? Solid. So what is the pertinent one? Consider next. Consider. Tell me. Zn plus HAPO2. Good boy. So this way. Next one. Here also some message I will give you. I'm going to consider the equilibrium. Right? Always the equilibrium. Let's consider the equilibrium. Okay. Reaction. Don't write reaction. The equilibrium means reaction as well as equilibrium. Reaction means reaction. I'm not sure about its equilibrium nature. So interesting language. So let's consider the equilibrium. What equilibrium consider? Tell me. To hurry, because remember you have your target here. Oh sir, zinc oxide solid. Good boy. A good suggestion. Zinc vapor plus half O2 gas. Then get this, and this time I will not give you data. I will give you data though. Acha. It's a good boy. Acha, I'll tell you something here. Let me write here. Data I'll give you soon. K is what? K, same way, delta G0 available. So these are all available. Oh, without this, I cannot do myself. I cannot do this problem, solve this problem. In one way. Cannot. Okay? Data must be. Or you might say, you carry out experiments and you generate data. That is, of course, very okay. That is actually genius, work of genius. Okay, good boy. So K is what? Can I write quickly? PZN, PO2. So vapor means gas. That's good. Quickly. Unnecessary talk will actually waste time. Activity is done. What is this? What is this? This you love. Should be present. On. Simplifies. What is this value?
1.1.
These are all their simultaneous equilibrium, all actually compatible with anyone else. This value, final value, these are all compatible. Okay. So good boy, good, correct. This is what? Point. Oh, right. I have to write what else I can do. I do not know. 10 to the minus 5 powered half. Good boy. PZN, it is also known. What temperature always tag temperature for us not bad. What is that? 2000. I will give you this. Or PZN is out. The answer I am giving you. Answer is PZN. Write this with me. 2.607 atmosphere. 2 point, so that you can calculate yourself. But I give the data giving for this. I tell you what. This is given to you. This data. Don't know. This data is given to you. Zinc. This way it is given. Given. Zinc vapor plus, you have to answer this one. This is another lesson coming. Half O2 gas, the data manipulation. No new theory, data manipulation only. Oh, theory is always there. Tell me what is that theory. This delta G0 is given to you. Can you recognize this reaction for the timing? This is a very popular type reaction. What type? Popular type. Let me know. I am writing in the meantime. Oxidation is actually formation reaction. Such a thermodynamic term. Formation, nothing like formation. You have to live with formation. You ask formation reactions. You can only ask formation. Then you plug them suitably. Formations. All heat of reactions can be written in terms of formation. I taught you. So what I taught you have to go back actually. See, two different ways of the writing enthalpy change. Formation is very useful, very useful. Delta G0, good boy. Delta G0 is, suppose I write you, minus, I have to answer this, minus 4, quickly, it is better, 4, 8, 920, minus 18.80 TLNT, minus 18.80 TLNT, happy? And what else, plus 344.7 Joule. These three terms, these runs 3 terms, not 2 terms. This is unusual. Not unusual. 5 terms will be there, but this is 3 terms. Okay, we'll consider 5. So,
1.80 T log.
yeah, log T. Thank you. Please ask me. Please do ask me. I'll be very happy. So, is it okay to now? Now, Doma will ask you, what is the delta G0 gives us care? Delta G0 is what? For this delta G0.
Temperature.
Delta G0 is what? Delta G0 what? Expression for delta G0.
Plus 50.
It is. This is something is given to you. In a sense, it is given to you. So you cannot say, sir, A plus BT type. It is giving, data giving. See what is given and what is required. Opposite sign, because it is zinc to zinc oxide. Zinc plus half of this zinc oxide to zinc. You may consider this also. Same result. It is up to you. Up to, when I say up to you means what a good news. Okay, how happy you are. How nice. It is up to you. Means either you can consider this, you consider the opposite. What is this? What is the opposite? Tell me. I am one case I am showing. 4 opposite. And then plus 18 TLNT plus 344 point. No, minus. Tell me correctly. So I'll show you if you use this and if you use that same result, how can it be? So it is negative and with the opposite sign, plus plus minus though. So this gives you k. The value I have given you, I don't know, I don't think so. This value. So what I'm trying to tell you, I'm telling you, if you write here, suppose, I'm telling you, k is, I'm giving what is precedent though. K, follow, very interesting here. K is what? K will be how much? Can you guess? You cannot guess actually. K will be very difficult to say. No. I'm writing here. Just some additional question, additional talk, additional feature, additional talk. Not bad. I'm admitting it is additional talk. What is this additional talk? What is the precedent? What is the K? K here? Tell me. Is knowing the answer? Knowing the answer? K is nothing but knowing the answer. 2.607. Take a look. Take a look. Knowing the answer, this times. Tell me. 1058 times 10 to the minus 5 square root. No doubt though. This is the K. Right? K. Call this K 2000. So this is the answer. Now you say, suppose NASA, I will use this. Is it formation reaction? Reverse of the first. Maybe. But when see how say reconcile, sir, whatever I wish, I said it is up to you. Suppose you wanted this, since you wanted this, but if you wanted this, you want this, but if you wanted this, then what is this K? Remember, note delta G0 is minus RTL K. So here also delta G0 is minus RTL and K. So positive and negative, what happens to K? One is 4. 4 is plus RTL and K, minus 4 is RTL and K. These two K is same. Log is there, reciprocal. Reciprocal will make this. This K and that K will be reciprocal. Is it okay though? So this can I write here? K say K in this case. Right here, okay. So so right here I am writing here K 2000 here. This case, K 2000 will guess the reciprocal of this. What is the reciprocal value? Tell me. You wrote here a moment ago. So write 1 by, write nicely 1 by 2.6. Follow this. One lesson and whole life. One lesson and whole life. And whole life. Happy though? Now what is this? Now see, giving this K value. Tell me what is this? Tell me here. Here. No doubt. See delta T0. Log, negative change means log what? Log makes what? Log K, delta G0 negative. So means log K will be must be log K. What is this K? Log K. This K will be reciprocal of this. The first one. Reciprocal means again get a negative sign. Minus plus get back to this. So it is a good demonstration. So what is the K? Tell me now. Given now, this value is given. So what is the expression? Your aim is to find PZN either this way or this way. I am just demonstrating whole life. You have no confusion or anything, sir. Result same. Delta K is not same, but K expression of K is different. In the same way, it is different. If it is reciprocal, expression is also inverse. And of course, it is inverse. See what is this? Right? Therefore, activity of zinc oxide. See here. Zinc oxide here. PZN, PO2, power half is power half. This is 1. And this value is what? This value you have considered. K is how much? Right here. Write this 1.2607 once more. Right? Times 1.058 times 10 to the minus 5 whole power half. You write this because I cancel soon. Okay, that's why I'm not so worried. Is what? This is also what? What is the PO2? PO2 is how much? Right here. This one. You write here. Please write here. PO2. I'm taking some trouble though, but it is whole life confusion over. Half. Will you not cancel this and this? What remains? 2.607 and 1 by PZN. That leads to what is the PZN? 2.60. Same result. Right? Same result. So you may consider any reaction, forward or formation or reverse of formations. So you may consider same result. Okay, this is one lesson you understood. But what normally is given, that was no formation. Formation is actually heat of formation is very important thermodynamic data, and in the formation, and you can now apply to any reaction. Oh, happy. Okay, so this is over data I have given, but the calculation actually I have not done because this one I have not done actually. Delta G I have given, you have to do yourself. Can I remove this? Next equilibrium is what? How many out? How many out? PZN. See, how many out? PZN out, PH2S and PS2. Now suggest me which one I consider. Nirjar will suggest. I am good boy. ZNS, right. ZNS and what shall I do? Tell me. I am very happy.
ZN plus half.
100%. Half H2. Very good indeed. Because you have to involve. See, point is involve sulfur. Otherwise, how will you get sulfur? Anything like anything. So if I want to sketch is zinc sulfide, zinc vapor to zinc sulfide, zinc. These three I consider. They are actually kind of in the system, satisfying each other. Good boy. So you can do yourself. I'm now actually time is. I will not take much time. K is what? Tell me again. PZN, PS2 quickly. I'm giving you actually how to proceed. Again, I have considered this. What is the activity? K2000. This is known from delta G0. PS2, PZN how much? Substitute PZN how much? Tell me. PZN is a moment ago 2.607. Write this. Sorry, 2.607. This leads to PS2. What value PS2? Answer 0.357, 356. Is it very happy? Okay. And what last one? Okay. Now, what else I shall ask you?
H2 plus half H2.
Acha, suggest someone. Okay. Acha, yeah, you suggest. Supalan suggest. This is okay. She's 100%. In fact, I will also do this. But see, alternatively, try to solve a problem in a number of ways, then you don't have to solve many problems. One problem, take up a number of ways. See, every time I'm doing the alternative, it takes time though, but your concept is very clear. Okay, so yeah, you want to get the value of sulfur alternatively. What equilibrium you may consider other than this? Involving sulfur. See here. Zinc sulfide. Think.
Zinc sulfide plus O2.
Two. Possible. The ordinary sulfur dioxide.
H2 plus H2. Half of H2.
This is right. Alternatively. I'm writing, but you will not go for this. But concept clear. Knowing everything, I will go for the shortest route. Zinc sulfide solid. Yes. Anurag, tell me what right? Hydrogen gas. You wanted to mean this, or what else?
I say that H2 plus H2.
That's H2.
Plus half of H2 is H2S.
But you have a difficulty. You don't know the H2S yet. That you will do later, in fact. H2S, see, only one must be unknown. Your target is sulfur, so H2S must be known. You don't know yet. In fact, you will use this later on. It is correct suggestion. It's okay though. It is okay though. This okay. Alternatively consider. But I will not consider the reaction. Equilibrium. I also equilibrium better term. When it is equilibrium better term. But I will not do this. I will not go for this. I will give you this, but I will not go there. I will give the data here. Then okay. Please take the data. Zinc sulfide. What is the zinc plus sulfur? Too? Zinc sulfide, zinc plus sulfur. Please delta G0. Delta G0 is. Yes, there won't any question. Tell me freely. No, I don't mind that.
You have written that equation. How did you identify the equation?
This one, this delta G is different. Delta G,
And this is not a formation reaction.
No. Just formation reaction, formation data are available. I will give you. I'm writing delta G0. Acha, very good, very good question. I'm coming to this. First of all, let me finish this. This delta G0 is what? Let me write this. The zinc sulfur as I'm going to write, in fact. 397400. 400 plus 14 point. When you ask question, I'm very happy. Remember.